Hello students, myself Vivek Kumar Gupta. I am assistant professor at computer base at IIMT College of Science and Technology, Greater Noida. So today's in this lecture we will discuss about the numerical differentiation. So before discussing numerical differentiation, we will discuss about some associated terminology. So first let's discuss about interpolation. So what is an interpolation? So interpolation, or why it is used and where it is used. So interpolation is used to estimate intermediate values between precise data points. So suppose we have given a data points in a tabular form. Suppose it's a the given data is suppose yielding of rice of last 10 years. So we have data suppose from 2001 to 2020. But in some situation by our sub human error, we have not the proper data of the 2007. So how we are going to estimate the given data uh, by the given data? So we have the data from suppose like 2000s to 2001 to 2020 or 2011 to 2020, but we have not 2017 data. So by using the interpolation method given by the numerical methods, uh, we can find out the value within the given precise data points. So how we are going to find the missing data values? So we first fit a function which are in the form of polynomial or in the form of other values. So we first fit a function that exactly passes through the given data points and then evaluate intermediate values using the function. Or the function which interpolate the value, we can call the interpolation function, which used to interpolate with the through a set of data points. So here we have given the two diagram for the interpolation. First is by using the polynomial interpolation. So the intermediate values between the given data points, the missing data, when we are finding the word we use the interpolation. But the value we have to find after the data points which are given. So suppose we have the given data from 2001 to 2020, and we wanted to estimate the data value of estimate value or function for the 2021, which is not the given case, which is not the intermediate case. So then we can call that the extrapolation of for the given data. So there are many methods to interpolate a function or interpolation function, which are categorized in the like polynomial interpolation or spline interpolation. Here we are using two general polynomial interpolation. So what are the purpose for the interpolation? In numerical methods like tables, the values of the In numerical methods like tables, the values of the function are only specified at a discrete number of points. A discrete number of points means number of points which can be countable, not in the form of intervals like 2005 to 2010. So it is in the form of intervals. But in the category wise, like 2005 data, we have given 6, 7. That is defined as a discrete number of points. Or so using interpolation, we can describe or at least approximate the function at every point in this space. So purpose of numerical methods for interpolation. So we can use interpolation to plot smooth curve through discrete data points which are given, and then here we can see that in interval there are 3 points are given, that is represented by the red dot, and we have interpolated or we have approximated a polynomial curve. So this approximation can give the value of the data within the red points. That is defined as interpolation. Okay, so we can by using the interpolation we can draw a or plot a smooth curve through given discrete data points, and the joining by the discrete data points we can plot a curve. So we can find the intermediate values values of the by the given data curve. Also, we can read between the lines of table. So if we have if we have plotted the curve using discrete data points, we can understand how it is rising, how it is changing the value or the function of curve through the given data points. Okay. Also, we can interpolate values from computation, so we can find the value of the missing data or which are not given in the tabular form. Also, we can develop some numerical integration scheme and also numerical differentiation scheme. Okay, so when we have interpolating function, we can find the numerical integration and differentiation methods. So interpolation is typically not used to obtain a functional description of measured data, since errors in the data may lead to a poor representation. Okay, but curve fitting to data is handled with a separate setup scheme. So for interpolation, we have defined some terminology. Let's define first of all difference operator. So let us suppose a function is defined, which is given, which is a function of x, and y0, y1, and yn are the values of y at x0, x1, x2, xn respectively. Okay. Then the difference yn minus y0 or y2 minus y3 are called the first forward difference of the function y. They are denoted by del y0, del y1, del y2. So suppose we are finding del y2, then that means as the name suggests, forward difference operate difference. So del y2 means the forward number of y2 is y3, and the difference y3 minus y2 is represented by del y2. So general format of forward difference operator we can describe as if del yn is equal to yn plus 1 minus yn. It is true for all the in n0, 1, 2, 3. And the symbol that is called a forward difference operator and pronounced as delta. Okay. Similarly, we can define another operator which is named as backward difference operator. So as the name suggests, so this is the symbol which is called nebula, but here we can say backward difference operator operating over yn. So as the name suggests, yn minus 1 is defined as the backward difference operator. So for the first interpolation formula, which is given, already we know that, because we are going to discuss the numerical differentiation. So we have using the given formula like Newton's forward interpolation formula, which is defined using the difference operator, and which is also a polynomial interpolation formula. So it is defined as y is equal to y naught plus p delta y naught into p plus p into p minus 1 upon factorial 2 del square y naught, something like that. And Newton's backward interpolation is given by this formula. So y is equal to, here we can see the difference between Newton forward and backward interpolation, as the Newton backward has the last value of the function yn, and the Newton forward is starting from the first function or y0. Okay. So how the interpolation formula works? So we are going to understand by using an example. So first, suppose an example. So here the table of given distances in nautical miles of the visible horizon from the given heights in feet above the surface. So here the height and distance are given, and for the 100, 150, and distance is also given. So we have to find the values of y when x is equal to 160. So we can see that the height are in equal intervals, and the value of these x are given in the form of distance. We have to find the value between 150 and 200. And the data we have to find, which is x is equal to 160. So we are going to interpolate the polynomial by using the first Newton forward interpolation formula. So for applying Newton forward formula, we have to first create a difference table. So suppose the given data is, we can write in the column x is 100, 150, and this is, and y is the distances. So first a difference operator applying on the y is, so first is y0, which is given by y1 minus y0. So 13.03 minus 10.63 will give 2.40. And then del y1, which is given by the 15.04 minus 13.03, which is 2.01, and so on. And the second difference operator will find by subtracting 2.01 minus 2.40 and the 1.7.7 minus 2.01. Similarly, the third difference operator and fourth difference operator. Okay. So let me repeat again. So first difference operator will find like del 2.40, which is del y0, which is given by the difference from 13.03 minus 10.63. So 13.03 is y1 and 10.63 is y0. But here in this case, we have to find x is equal to 160. So we can suppose y150 as y0 or initial point. Okay. And if y0 is equal to 150, so sorry, x0 is equal to 150, then y0 is 13.03, and then respectively we can change all the values, or we can name all the values. So if y0 is equal to 150, then y1 is, sorry, x0 is equal to 150, then x1 is 200, x2 is 250, and x3 and so on. And the corresponding value and the corresponding difference table are formed as we define the number name. So if you take x0 is equal to 160, then y0 is equal to 13.03. Here x0 is equal to 150, so y0 is equal to 13.03. And accordingly del y0, del 2y0, del qy0, and del 4y0. Since x is equal to 160 and h is equal to 50, h is the difference between these two numbers. Okay, and p is the difference x minus x naught upon h. So here x is equal to 160 and x naught is equal to 150. So x naught is equal to 150. So difference will be 10 upon 50 is equal to. So here. So either here a missing value is 150, not 160. Okay, so it is a typing error. So x naught will be 150 and x is equal to 160. Then we will find the value of p. Okay. Okay, so we have to interpolate the value of y is equal to 160. So by using Newton's forward interpolation formula and by using the difference table, we can put the value of y0, del y0, and del square y0, and so on. So by substituting those value, we have find that y160 will be 13.46, which is accordingly the table. So we can see that at 150, the value is 13.03 and 200 is 15.04. So 160 is between the 13.46, which is in between the value of given data. Okay. Now we have to define numerical differentiation. Okay. So what is numerical differentiation, or what is numerical differentiation, and what does it mean and where it is uses numerical differentiation? Let's suppose. So first question or motivation we have to for the numerical differentiation is how do we evaluate the derivative of a tabulated function, and how do we determine the velocity and acceleration from tabulated measurement. So differentiation, as we know that differentiation means rate of changes in the case of distance, or in the case of case of distance, derivative will be represented by velocity, and double derivative will be represented as acceleration. So suppose we have, as in the case of interpolation, we know that we interpolate by using the discrete data in the form of tabular. So as we have discussed, that suppose we have given the yielding of 10 years, last 10 years, which are written in the form of tabular. So how we are going to find a derivative if the function, if the value are given in the tabulated form. So in the first case, so what are the goal of numerical differentiation? So the goal of numerical differentiation is to compute an accurate approximation to the derivatives of a function. Okay. And for given measurement, which are in the form of tabulated data, okay, for given measurement of the underlying function fx at the node value is this. And the task is to estimate f dash x of first derivative and the later higher derivatives in the same nodes. Also, so what are the strategy? So by using, we have already seen that to interpolate or to extrapolate a value which is not missing in the tabular form, we can define a polynomial interpolation or a spline interpolation or a different interpolation, which give an interpolating function which in the form of polynomial or other form. Okay. So by using, as we have discussed example in the form of, so here are some interpolation formula which are in the form of polynomial. So Newton's forward interpolation on backward interpolation formula, which are used to find, interpolate, or which are used to interpolate or extrapolate the data. Okay. So, so our strategy to find a numerical differentiation. So first we have to fit a polynomial by cleverly selected subset of the nodes and use the derivative of that polynomial as the approximation of the derivative. So we have given the Newton's forward differentiation formula. We have given Newton forward interpolation formula, and now we are going to find derivative of the Newton's forward differentiation formula. So as we have given Newton's interpolation formula, let's find a derivative of this interpolation formula, which are used to find the differentiation of tabular data. So differentiating both sides with respect to p, we have dy upon dp and y0 as a constant, so it will be 0, and p into del y0, so del y0 is a constant, which will give dp upon dp1, and similarly, so p square minus 1 will be given 2p minus 1 upon factorial 2, and del square y0, all the del value or delta value is a constant, so we'll differentiate only the p polynomial of the p. And since we know that differentiation is a linear operator, so it will differentiate linearly in each terms of the del operator. Also, we know that since p is equal to x minus x naught upon h, therefore dp upon dx is equal to 1 upon h. Now, dy, as we can write in the using dy by dx is equal to dy upon dp into dp upon dx. So from this, we have calculated dy upon dp is this, and dp upon dx is equal to this. So by multiplying, we can write dy by dx as in the form. Okay. So dy by dx will be this. So suppose if you are putting p is equal to 0, okay, then it will convert in the form of equation 1. Again, differentiating 1, we can find out the double derivative of the function. So suppose we are differentiating again with respect to y, the given function, we can write d upon dp, dy upon dp, and dp upon dx. So dp upon dx is given by this is equal to 1 upon h. So we are differentiating again this function dy upon dp with respect to p. So so As we know that del operator are constant, will give constant. So first it will be 0 and 2p minus 1 will give 1. So del s bar y0 and so on. Okay. So dy by dx square is defined as equation 2. Similarly, we can find the third and second, the third and fourth and so on derivative as we are needed or as we are required. So simply we have what we have done in numerical differentiation. So the first step we have done is that if we have given the tabular data. So first we are using uses of interpolation formula which are in the form of polynomial or a spline, whatever. So first we interpolate the use the interpolation formula, and then we'll use the differentiation, simple differentiation to the interpolation formula which uses to interpolate, and simply then we can find the value of numerical differentiation for the missing value or the required value. So for the given data. Okay. Okay. Now we are derivative using Newton's backward difference formula. As we have discussed, Newton's backward interpolation formula is given y is equal to yn plus p nebula yn plus p into p plus 1 upon factorial 2 nebula square yn plus p into p plus 1 p plus 2 upon factorial 3 nebula cube yn plus and so on. So differentiating both sides with respect to p, we have this formula. Here we know we know that p is equal to x minus xn upon h. Therefore, dp upon dx is equal to 1 upon h. Now, similarly, we can find as we have differentiated numerical forward interpolation formula, dy upon dx. We can write dy upon dx is equal to dy upon dp into dp upon dx, which is given by this. And if we putting the if x is equal to xn, at x is equal to xn, p is equal to 0, and p is equal to 0. So in this, why we are using x is equal to xn? So suppose if we have given, we cannot find a numerical differentiation for the missing value of data. We can find only for numerical differentiation for the given discrete data. Why? So since we have suppose we have a missing value, so we are not accurately know the function nature of the function, whether the function is continuous or not at the missing value. So we cannot say the function is defined or whether or not defined or continuous at that point. Therefore, we can find numerical differentiation at only the value we have known already. Okay. So by numerical differentiation, we can find the rate of change at the given data which are given in the tabular form. Okay. So that's why we are using after differentiating, we are substituting x is equal to xn, which give p is equal to 0. So x is equal to xn, why we are substituting x is equal to xn? Because we can find the derivative only for the known value of data here. Okay. So at p is equal to 0, so we can see that p is defined as x minus xn upon h. So when x is equal to xn, it will give 0. So by putting this, we'll find the equation of 3, which is the numerical differentiation of Newton backwards interpolation formula. Similarly, we can find double derivative and triple derivative of the given function or given interpolation formula. Okay. So let's do an example. Okay, for the numerical differentiation. So suppose the following data gives the velocity of a particle for 20 seconds at an interval 5 seconds. We have to find the initial acceleration using the entire data. So time is given, which is equally distributed, and the velocity is also given. Okay, so we have to find at the interval 5 seconds. When time is 5, what are the differentiation or what are the acceleration at the find. Here velocity is given, so we have to find the velocity differentiation of velocity function. As we know that differentiation of velocity with respect to time will give acceleration. So first we find the difference table. So as t is given and v is also given, so we'll find the difference table with respect to v. So del v is difference from 3 minus 0 to 3, 14 minus 3, 11, 69 minus 50, 14, 55. Similarly, del 2 v is 11 minus 3, 44 55 minus 11, 44, and so on. Now for initial acceleration at t is equal to 0 is required. We use Newton's forward formula, that is dv by dt, which is given by this, and the velocity or acceleration at time t is given by this. Okay, so thank you. So what we have discussed in this lecture, so let me recall or repeat again. Just so we have discussed the numerical differentiation by using the interpolation. So when we are going to find numerical differentiation, so suppose we have given the discrete data or in the form of tabular. In some cases, some data are missing. So we'll interpolate a function which is in the form of polynomial or which give a function that is called interpolating function to interpolate or extrapolate the missing value data. Okay, and then we'll find the value of function value. Okay, and then we'll find that after differentiating the interpolating formula, we are going to differentiate by using simple differentiation, and by the value which is given already, we can find the differentiation at that point. Okay, so thank you.